In this mini-lecture, which is part 2 of the mini-lecture on air pollution, we will discuss air pollution further, the effects of air pollution, and U.S. laws and regulation related to air quality laws. After reading Chapter 17 and watching this videos or reading the transcript that goes with this video, you should be able to explain stratospheric ozone depletion and identify steps to address it, define acid deposition, illustrate its consequences and explain how we are addressing it, and characterize the scope of indoor air pollution and assess solutions. Thanks in large part the Clean Air Act, originally written in 1964, but amended in 1970 and 1990, air quality in the U.S. has significantly improved. The Clean Air Act funds research for pollution control, sets standards for air quality, limits on emissions, allows citizens to sue parties violating the standards, and introduced a cap-and-trade program for sulfur dioxide. The Clean Air Act gives the EPA the authority to set standards for emissions through national ambient air quality standards. These are standards for any pollutant that may be harmful to human health. Most states have an agency that monitors air quality and other environmental conditions, and reports back to the EPA. The EPA, on the other hand, develops, implements, and enforces environmental regulations that the state agencies must abide by. States submit their plans for monitoring pollutants and adhering to the regulations to the EPA for approval. In Texas, we have the Texas Commission on Environmental Quality, abbreviated TCEQ. If the EPA can take over monitoring at the state level if it determines that state plans are inadequate. As can be seen in the two graphs on the left of this slide, total emissions of the 6 monitored pollutants have declined significantly since the Clean Air Act of 1970. This reduction comes despite increased population, energy consumption, miles traveled, and gross domestic product. Other things that have helped reduce air pollution include federal policies and technology. We now have cleaner burning engines thanks to catalytic converters. Catalytic converters filter pollutants from vehicle exhaust. The hydrocarbons, carbon monoxide, and nitrogen oxides produced by the burning of gasoline in the engine are removed by the catalytic converter, and in their place less harmful gases such as carbon dioxide, water vapor and nitrogen gas are released. Clean coal technologies, such as the diagram of the scrubber in this slide, have also been helpful in reducing air pollution. Finally, federal permit trading programs are also very effective. Recall that the program for sulfur dioxide was largely responsible for reducing sulfur dioxide emissions below the target level. The reduction in outdoor air pollution since 1970 is one of our greatest accomplishments as a nation. But despite the fact that concentrations of all the criteria pollutants, except tropospheric ozone, have fallen well below the health and safety standards set by the EPA, there is still more we need to do. There are now concerns over new pollutants and greenhouse gas emissions. For example, U.S. carbon dioxide emissions increased 44% between 1970 and 2008. In 2012, the Supreme Court ruled that the EPA could regulate carbon dioxide as a pollutant. However, there is formidable political opposition to this ruling. Consider this though. We were able to reduce emissions of many major pollutants by 60% while expanding our economy. Why couldn't we do the same thing for CO2 and other greenhouse gases? We have also reduced emissions of toxic air pollutants, which are pollutants that cause cancer, reproductive defects, or neurological, developmental, immune, or respiratory problems. The EPA regulates 188 toxic air pollutants. Examples of toxic air pollutants include mercury from coal-fired power plants, VOCs such as benzene, found in gas, and methylene chloride in paint stripper, including mercury, VOCs, methylene chloride. Toxic air pollutants cause cancer, and 1 out of 28,000 Americans' Clean Air Act regulations have helped to reduce emissions of these pollutants by more than 35% since 1990. I have mentioned smog several times in this mini-lecture now. Let me now fully explain what smog is. Smog is an unhealthy mixture of air pollutants that forms over cities as a result of fossil fuel combustion. There are 2 types of smog: industrial and photochemical. We will examine each of these separately. Industrial smog results from fossil fuel combustion. When coal or oil is burned, a portion of it fully combusted, while the rest is either partially combusted or completely unburned. During the process of burning fossil fuels, sulfur dioxide is formed. Industrial smog is composed of this sulfur dioxide, small amounts of sulfuric acid, and the particulate matter produced from burning fossil fuels. Carbon dioxide and carbon monoxide are also in industrial smog. Industrial smog is colored black-brown and can settle as haze over industrial cities. Industrial smog can turn deadly when combined with thermal inversion. Thermal inversion is a common type of inversion that occurs in mountain valleys where slopes block morning sunlight and keep ground-level air in the valley shaded and cool because cooler air at the bottom of an inversion layer is denser than the warmer air above it. The air resists vertical mixing and remains stable. Vertical mixing is needed because it allows air pollution to be carried upward and diluted. Thermal inversion, however, traps pollutants near the ground. This happened in London in 1952. The smog that formed there was called the killer smog because it killed between 4,000 and 12,000 people. A similar event happened in Donora, Pennsylvania in 1948, during which 21 people died and 6,000 people became ill. The second type of smog is photochemical smog. This type of smog forms when primary air pollutants from automobile exhaust reacts with sunlight. The sunlight drives chemical reactions between the pollutants and normal atmospheric compounds and results in the production of over 100 different chemicals, with tropospheric ozone being the most abundant of the compounds produced. Photochemical smog can also be exacerbated by thermal inversion, which is why Mexico City, a city that is both in a warm climate and in a valley between mountains, suffers from photochemical smog. We have reduced smog in the U.S. This graph shows peak levels of tropospheric ozone in Los Angeles from 1970 to 2010. Notice that the level of ozone has gone down over the decades, but it unfortunately still exceeds state health standards. The reductions were a result of a variety of factors, including pollution control technology, vehicle inspection programs, financial incentives to replace aging vehicles, cleaner burning fuels, cleaner industrial facilities, pollution indicator boards, and alternative transportation. Restricting driving and closing industrial facilities that cannot clean up their emission are also effective strategies. However, these two methods are less popular with the public and industry, respectively. If we are not careful, though, our gains in air pollution reduction may be cancelled out by the increased number of cars on the roads caused by a growing global population that is steadily becoming industrialized. Let us now examine stratospheric ozone. Recall that ozone in the lower stratosphere absorbs the sun's ultraviolet, UV radiation. Without the ozone in the stratosphere, a great deal more UV radiation would reach the Earth and cause damage to biological tissues and DNA. Our air pollution, however, has caused the ozone layer to become smaller, and in some places holes have formed in the ozone layer. The pollutants that cause this damage are called ozone-depleting substances. These are human-made chemicals that destroy ozone. The two main culprits are halocarbons and chlorofluorocarbons. Halocarbons are human-made compounds made from hydrocarbons with added chlorine, bromine, or fluorine. Chlorofluorocarbons, also known as CFCs. Halocarbons used as refrigerants, in fire extinguishers, in aerosol cans, etc. CFCs were widely used once because they have incredibly high boiling points, which means they could be used near high heat sources without the risk of them catching fire. Recall from earlier in this mini-lecture that some pollutants have a very long residency time. CFCs and halocarbons are compounds that stay in the stratosphere for at least a century. We assume CFCs were harmless because CFCs rarely react with other chemicals, but because they are non-reactive they reach stratosphere unchanged and can linger there for a century or more. CFCs essentially strips ozone of one of its three oxygen molecules. When this happens, ozone is turned into O2, which doesn't have the same UV absorption and reflection qualities. The problem with CFCs is that one molecule of CFC can destroy 100,000 molecules of ozone, and since CFCs stay in the atmosphere for centuries, this problem is difficult to stop once it's started. The ozone hole is a vast area of thin ozone in the stratosphere situated over the Antarctic region. Please understand that ozone depletion lets in more UV rays, but this doesn't appreciably warm or cool the atmosphere. Also, there is a misconception regarding the ozone hole and global warming. The common misbeliefs are that 1. Depletion of stratospheric ozone helps to prevent global warming by letting heat or gases out, and 2. Ozone depletion lets heat into the atmosphere. Both of these are not true. Although the Antarctic ozone hole grew quickly after it was observed in 1985, the phase-out of ozone-depleting compounds beginning in 1987 has stopped the growth of the thin area of ozone. The Montreal Protocol of 1987 is the main reason why this happened. In 1987, 196 nations signed the protocol and agreed to cut CFC production in half by 1998. Later agreements deepened cuts, advanced timetables, and addressed other ozone-depleting chemicals. Following the Montreal Protocol, industry shifted to safer alternative chemicals. Although we stopped the Antarctic ozone hole from getting worse, we still face challenges because CFCs will remain in the stratosphere for decades or longer. We can remain positive though because the Montreal Protocol can serve as a model for international environmental cooperation. I'd like to now turn our attention to the problem of acid deposition, commonly known as acid rain. Acid deposition is the deposition of acid or acid-forming pollutants from the atmosphere onto Earth's surface. A simple way to think of this is that acid precipitation is any form of precipitation that is more acidic than normal. Acid deposition is one type of atmospheric deposition, which is a broad term referring to the wet or dry deposition of a wide variety of pollutants, including mercury, nitrates, and sulfur. Acid precipitation is an example of a secondary pollutant because it is formed from primary pollutants. For example, industries that burn fossil fuels emit sulfur dioxide and nitric oxides into the atmosphere. The pollutants combine with water, oxygen and other oxidants to form sulfuric acid and nitric acid, which fall to the earth from the atmosphere in the form of acid rain. Acid rain has a variety of impacts on the earth. The following are the main effects of acid rain. It causes nutrients to leach from topsoil, changes soil chemistry, converts toxic metal ions, such as aluminum and zinc, into soluble forms that pollute water, affects surface water and kills fish, damages crops, erodes stone buildings, corrodes cars, and erases writing on tombstones. We have reduced acid rain through the Clear Air Act amendments of 1990. These amendments established an emissions trading program for sulfur dioxide that drastically reduced the incidences of acid rain. New technologies such as scrubbers have also helped. Altogether, policies and regulations have lowered U.S. emissions of sulfur and nitrogen oxides 43% since 1989. However, like many environmental problems, acid deposition is worsening in the developing world. For example, coal-burning China emits the most sulfur dioxide and has the world's worst acid rain problem. We have focused this lesson on outdoor air pollution, but it's important to recognize that there are significant threats to our health brought on by indoor air pollution found in workplaces, schools, homes and other buildings we spend a lot of time in. Considering we spend 90% of our time indoors, we should be aware of the air pollutants we are exposed to while there. The WHO estimates that 3.5 million people die prematurely because of indoor air pollution. Compare this number to the 3.3 million people who die from outdoor air pollution, and it's clear to see indoor air pollution is just as significant as outdoor air pollution. In the developing countries, the major indoor air pollutants are produced from burning wood, charcoal, manure, and crop waste for heat and cooking. The buildings in developing countries usually lack adequate ventilation, so people are exposed to dangerous amounts of soot, carbon monoxide, and other pollutants. In the developed countries, the major air pollutants of concern are tobacco smoke, radon, and VOCs. In many places though, smoking is no longer permitted indoors, so this helps to reduce the risks associated with this pollutant. Radon is a natural radioactive gas that is formed by the decay of uranium in the soil, rock or water beneath a building. You should also be aware that indoor air pollution can be caused by tiny living organisms. Dust mites, airborne spores of fungi, molds and mildews can cause allergies, asthma, and other respiratory problems. Microbes that induce allergic reactions are suspected of being the main cause of sick building syndrome. This is a sickness produced by indoor pollution for which the specific cause is not identified, but it is hypothesized that microbes and VOCs play a significant role in this illness. To keep yourself safe from indoor air pollutants and sick building syndrome, you can limit use of plastics and treated wood, use low-toxicity building material, furnishings and products, limit exposure to toxic substances, test homes and offices for radon and mold, use carbon monoxide detectors, and keep rooms and air ducts clean and free of dust. That concludes this mini lecture on Part 2 of Atmospheric Science, Air Quality, and Pollution Control. If you haven't done so already, please watch Part 1. Please review the weekly outline and complete the activities for this week per the schedule set forth in the outline.